One.
All right, so we got function composition. Function composition is an operation. Composite functions are what we're going to end up with after that operation. Okay, so function composition is the operation we're going to be dealing with some today. And then a composite function is what we're going to end up with. And when we talk about any kind of function, we're going to talk about all those things that we talked about with functions every time. Domain, range, intercepts, asymptotes, as we talked about rational ones. All those things are still going to be in play here. So we're just building up even more and more stuff here. But composite functions is really based out of function value is where we start with that. So that's what these first two examples are, is talking about function value. So how do we find f of 3 if f of x is 6x minus 7? Just plug it in for x, yeah. F of 3 would be 6x minus 7, and then, or 6 times 3 minus 7 now. That's what we're going to plug in. So that'd be 18 minus 7 would be 11. F of 3 is 11. So that really creates this ordered pair, 3, 11, as an ordered pair there. So that's function value. Maybe we've got a rational function there. G of x is 3x over x minus 5. And we want to find the function value in G for G of negative 4. So same thing, just plug that in for x. Excuse me, that'd be negative 12 over negative 1. No, negative 9. And then reduce that positive or negative? Positive 4/3. And again, that creates this ordered pair, negative 4 and then 4 over 3. Okay, so function value, a little bit of review there, because we're going to use that some as we talk about function composition. All right, so I'm going to teach this as if you've never seen it before, because I'm not sure if you did in Algebra 1 or Algebra 2. It's not that terrible. If you did see it, it's pretty easy. It's good review, but if you haven't seen it, it's not too bad. Okay, function composition. It's got its own little notation. It's this little circle. It's not the letter O. It's not a degree symbol. It's kind of right there in the middle. F composed with G of X. Looks like the word fog. So, why are you doing that? Returning to our mission of function composition. Function composition. F composed with G of X. That's what that is. All that means is you're taking whatever function is listed second. G of X function is listed second, and you're putting it into the first function, like function value. Okay? F composed with G means you're going to take the G of X function and you're going to replace X in the F of X function with it. Okay, we'll look at some examples of that. Need to go ahead and define the domain here, because that's what we're going to do first. The domain on a function, a composite function, is the set of all numbers, and if we're talking about domain, what letter are we referring to? X in the domain of G of X, and I'm using G of X here, but really I mean the second function, such that G of X is in the domain of F of X. And again, I'm saying F of X, but I mean the first function, because sometimes they swap that around, G composed with F, that sort of thing. Okay, so kind of wordy definition, but I think as we start doing some examples here, you'll be like, oh, well, that's not that bad. I can actually do that pretty good. All right, so let's start with a fairly simple one. Example C, let's say here's our f of x function, 2x squared minus 3. And then our g of x function is 4x. And we want to find f composed with g and state the domain. Yeah, we're going to compose that function. So f composed with g means we're taking g of x and putting it into f of x, just like the definition says. So the f of x function is 2x squared minus 3. We're going to replace this x with 4x. So that's 2 parentheses 4x squared minus 3. Space there. Okay, much more. All right, and then we could simplify that, obviously, with squaring the 4x. That'd be 16x squared times 2, be 32x squared minus 3. And we've simplified our f composed with g of x. That's what that composite function is. So let's look at the domain of that. All right, so when you're doing domain of composite functions, you really need to look at domain of each individual function, then look at the composite. Okay, for this one, it's not going to make any difference because the domain of both of those would be what? What's the domain of f of x? It's a quadratic. Every quadratic had a domain of what? Negative infinity to positive infinity. And then the domain of g of x, well, that's a linear function. No red flags that come up, no square roots, no x's in the denominators. So that was going to be from negative infinity to positive infinity. Okay, so there are no restrictions on either of these. So when we look at the domain of f composed with g, then it's going to be the same from negative infinity to positive infinity. We're going to see some in just a little bit here where the domains are different here. We've got to take that into account when we do our domain of our composite function. Okay, so get in the habit of getting the domain of each individual function first, and then we're going to use that to help us do the domain of the composite function. For this one, like I said, there's no restrictions, so it really doesn't do anything. But when there are restrictions, it can cause some things to happen. Okay. All right. So let's look at taking that particular example and looking at f composed with g of 2. What's that mean you're going to do? Plug that in for x, right, in our composite function. Since we've already found the composite function, that's what we would do. We would plug that into 32 times 2 squared minus 3. So that'd be 32 times 4, which would be 128 minus 3, be 125. Now, I want to show you kind of an alternative way of doing that. If you're just asked to find the function value and you don't, or the composite function value, but you haven't found that composite function yet, and maybe you don't want to have to do that, okay? So what you can do is remember that f composed with g of x, by definition, means you take the g of x function and plug it in to the f of x function. So what you could do is take, our f of x function was 2x squared minus 3, and then our g of x function was 4x. And think about order of operations here. Inside happens first, right? So I can plug in, I can find g of 2. Which would be 8. And then I would find f of 8. Which is still 128 minus 3, which is 125. We had the luxury of, we already had found that composite function. There's going to be times where they're going to ask you to find a function value of a composite function, and you don't have the composite function already done. And it's actually less work to do 2 problems than it would be to do the composite function and then plug in the value. But it comes out to be the same answer, 125. They match there, whether you do the composite function or not. All right. So keep that in mind as you work your way through there. What really, and a little bit more explanation there, what's happening. G of x is the same thing as what? Y. Y. Okay, so when we plug in 2 as the x value in G, 8 is the y value from G of x. Well, the y value from that function becomes the x value from f of x. And plug that in. So it's like reverse substitution. There's what's happening. You're taking the y value from one function, using it as an x value for another function, is what you're doing. So let's look at a few more of these functions. Example E. Let's say our f of x function is this, 1 over x plus 5. And our g of x function is 4 over x minus 1. Some rational functions. We just got through with that. So, really good stuff going on there. We want to find f composed with g of x and state the domain. Okay. All right, so let's work out f composed with g. So that means we're taking the g of x function and putting it into the f of x function, right? So 1 over 4 minus x minus 1 plus 5. Now, can we leave it like that? No, that's definitely not something we want to do. So what we want to do is get that in a little bit better rational form. Okay, so if I'm going to add 4 over x minus 1 to 5, what do they need to have? Same denominator, right? Common denominator with fractions. That common denominator would be x minus 1. So that gets us 1 over 4 over x minus 1 plus 5x minus 5 over x minus 1. And that simplifies to give us 1 over 5x minus 1 over x minus 1. Remember, dividing by a fraction is the same thing as multiplying by its reciprocal. So this ends up being x minus 1 over 5x minus 1. That's what f composed with g of x looks like. Just through some basic rational expression math there. Stuff you've done before there. So this is, a little bit more difficult because of the fraction stuff involved. All right, now let's look at the domain. Okay, and again, I want you to think about domain of f of x first. What would the domain of f of x be? And we don't necessarily have to do it in interval notation. Just tell me what we know about x. X can't be what for f? -5. We know that. And then on g of x, its domain, x can't be positive 1. Okay. Now, for our composite function, we look at that that domain. So this is the domain we're actually looking for. Domain of f composed with g of x. All right. Now, thinking about that, when I plug in the g of x can't be 1. So originally that's part of the restriction. So if that's a restriction on the first function that we're plugging in, then it's got to be a restriction on our domain of our composite function. So we know x can't be 1. Now the one that doesn't necessarily copy over is the f of x function, or the function we're plugging into. Okay, because when is g of x going to be equal to -5? That's what we need to know. We need a little bit more space here. This is the question we need to answer. When is g of x equal to -5? Well, the only way to decide that is to solve it. So solve that equation. So that'd be 4 is equal to -5x plus 5. Subtract 5. -1 equals -5x. X can't be 1/5. Now, notice on our composite function, if we set the denominator equal to 0, what can x not be? 1/5. This is the why that happens. Now, this is why you need to look at both of these, because if you just look at the composite function, you're going to lose the x can't be 1 if you don't look at the domain of each individual function. Okay, so we took what the restriction on x was for the function we're plugging into, and we set the function we're actually plugging into equal to that, or if we'll get some inequalities here in just a minute.
Is that where you're flopping around?
What do you mean flopping around?
G of x will be f.
G of x is what we're plugging into f of x. Okay, so we're looking at what can x not be on what we're plugging into, and we're setting what gets plugged in there equal to that. Okay, and that's where we're getting the 1/5 from. We could also get 1/5 from setting the denominator equal to 0 on the composite function, working it out. That's the same number, but we've got to be careful and not lose some things through simplifying. Because when you simplify a function, you know, it's like when we're doing rational functions, you could lose a vertical asymptote, right? When you simplify a rational function. So when we're dealing with rationals, a lot of stuff, comes into play that you got to be careful of, and losing values out of your domain are part of that. So let's write that domain in interval notation. So if x can't be 1, or 1/5, which one's the smallest number? 1/5, so it's got to come first. Union 1/5 to 1. Oops, forgot my u. 1 to infinity. And there's my domain of my composite function. Okay. We get some practice with this. It'll start hopefully making pretty good sense in just a little bit. It's the first example you've seen that's crazy like that. I'd say if you've seen function composition before, then you probably didn't do rational functions inside of it, most likely. Okay. All right, let's get another example. Let's say we had f of x is equal to the square root of x plus 3, and then g of x is equal to 2x plus 5, just plain old 2x plus 5. All right, so let's find the composition. Find f composed with g of x. Okay, and the domain, because the domain's the fun part, right? All right. So let's get that function composition out of the way. F composed with G means what's going into what? G into F. So instead of x plus 3, it's going to be 2x plus 5 plus 3, which we can simplify that to be 2x plus 8, right? And there's our function composition, or our composite function. All right. Then we need to look at domain. So let's look at the domain of the individual parts. Domain of f of x would be what? How do you find the domain of a square root function? Set what's underneath the square root greater than or equal to 0, right? So x ends up being greater than or equal to -3. So that's the domain for f. The domain for g, that was a little easier because it's just linear. And the domain for that linear piece would be -infinity to +infinity. So no restrictions on g of x. But there is a restriction on what we're plugging into. So we need to know when is the g of x function greater than or equal to 3. Okay? So we set 2x plus 5 greater than or equal to 3, or -3, excuse me, and solve it. X is greater than or equal to 4. This is our function composition domain. So the domain of f composed with g of x -4 to infinity. Oh, I screwed up my folder there. Now, keep in mind, that should be the same answer as if I took what's under the radical here and set it greater than or equal to 0. Is it the same? If I set 2x plus 8 greater than or equal to 0, do I end up with x is greater than or equal to -4? I do. I end up with the same answer there. Okay. Be careful though, you may lose some pieces if you just go straight to your composite. A lot of times it works, but you could lose some pieces if you go straight to the composite function. So be careful of that. All right. All right, let's take that same set of functions, these two here, and let's do the composition the other direction and see how it changes things. What I was doing there. There we go. Paste. This is example G. Find G composed with f of x. So same two functions, and we're going to go the other direction. We're going to look at composing it f into G and the domain and see how that changes things. All right. So let's find that function composition. 2 parentheses radical x plus 3 5. Not really anything you can do to that. It doesn't get any prettier. And there's our function composition. That one's an easy composition to make. Maybe the domain's just as easy, hopefully. Now, let's get the domain. So we're going to look at the domain of what we're plugging into. What's the domain of g of x? -infinity to +infinity, right? It's linear. It's a linear piece. Okay. So what that tells us is we're not going to have to do any kind of solving because there's no restrictions on what we're plugging into. When you have to do the solving is when there's restrictions on what you're plugging into. Okay, so we need to do the domain of what we're plugging in with. So we're going to look at x, square root of x plus 3. What do we know about that? X has got to be greater than or equal to negative 3, right? Just by setting x plus 3 greater than or equal to 0, that's what we get. Now, the domain of our composite function of g composed with f of x. There are no restrictions on the g of x function, so there's not anything I need to worry about there, but I do have a restriction from the f of x function. And it's that x has got to be greater than or equal to negative 3. That same restriction shows up in my composite function. There's a square root with an x inside of it, so we look at that, and it's going to be that same restriction. It came from the f of x function, though. So be from negative 3 to infinity would be our domain of our composite function. That's what we're looking at there. So when there are no restrictions on what you're plugging into, it makes the problems a little bit easier, a little shorter, maybe. Not as much you've got to do there. Just a couple of more examples here, guys. Hang with me. Let's get one that's got a rational function and then maybe a quadratic in it. So let's get h of x is equal to x squared minus 5x plus 7. And then k of x is equal to 3x over x minus 2. Okay. And let's do the composition h composed with k. I have no idea why I spread that out so much. Of x and domain. H composed with k of x and then the domain. All right, so good algebra workout here on this problem because we're taking k of x, which is a rational function, and plugging it into a quadratic function. So that's going to be 3x over x minus 2 squared minus 5 times 3x over x minus 2, and then plus 7. So what happens when I square this fraction? What happens to the numerator? Should be 9x squared. 3x times 3x, 9x squared. The denominator, if I square x minus 2, that just means x minus 2, right? Same thing as writing squared beside it. That's the same thing as if I multiplied it out and got a trinomial under there. I'm not doing that on purpose because I know what's coming next. Because I know if I'm going to write this as a composite function, I got to simplify it, right? So factored form in the denominator is what you want. Then the next fraction, there we got negative 5 times 3x over x minus 2. So that ends up being minus 15x over x minus 2. And I'll just put those in parentheses just to keep consistent. And then 7 didn't have anything happen to it. So if I'm going to make that look a little better, I need to get a common denominator. What would the common denominator be? X minus 2 and another x minus 2. Because the first one's got 2 of them. So that means everybody's got to have 2 of them. So this guy needs another x minus 2. And the 7 needs x minus 2 and x minus 2. So a little bit of work here. It shouldn't be too bad. So we got 9x squared. And then with distributive property there, it'd be minus 15x squared plus 30x. And then the distributive or over here, we're going to multiply x minus 2 times x minus 2. And that turns into x squared minus 4x plus 4. And to distribute a 7 to that, 7x squared, 28x plus 28. And then over x minus 2, x minus 2. Simplify the top. That'd be negative, that'd be just plain x squared, yeah, because that's 16 and negative 15 would be x squared plus 2x and then plus 28. That's good. Over, and I'm just going to rewrite that x minus 2 squared. So there's our composite function. A good little algebra workout to get that simplified function out of that. Now, let's look at our domains. All right, so we got to remember what we're looking at. Domain of h of x. We ought to be able to look at that and tell what it is, because it's quadratic. All real numbers, negative infinity to positive infinity. So anytime you see a linear piece or a quadratic piece, you ought to know those right off. You know there's no restrictions on what we're plugging into. Makes this problem easier, remember? So h of x domain negative infinity, positive infinity. Domain of k of x. Well, we had a denominator with an x in it. So the x minus 2 equals 0. You know, x can't be 2. So there's a restriction on what we're plugging in with. And so that'd be from negative infinity to 2 union 2 to infinity. So if there's a restriction on that part, that same restriction has to carry over to the restrictions on the composite function. So our domain of h composed with k of x would be negative infinity to 2 union 2 to infinity. Out of that. We don't have to worry about, you know, setting anything equal to anything because there were no restrictions on what we plugged into. There were restrictions on what we plugged into, then we would go from there. If this swapped order and we did the other direction, we would need to know, well, where is h of x equal to 2? And we'd have to solve that and hopefully get real answers for that. Let's look at one where maybe that happens. Last example of the day. Example h of x. Well, let's do f and g. I'm tired of h. I don't write those well. I had to fight to make myself write k instead of g. H of x, or f of x, is x squared minus 5x plus 7. Doesn't matter what they're called. G of x. Let's do 3x over x minus 2. Does it look familiar, right? All right. Now, let's do g composed with f. And we're going to find the domain as well. All right. So, maybe a little easier on the composition for this one, because we're plugging the quadratic into the rational instead of the rational into the quadratic, which I think is easier. So that gives us 3 parentheses x squared minus 5x plus 7 over x squared minus 5x plus 7 minus 2. And, you know, just distribute that out and see what can happen. What do we know about this quadratic here? Does it factor? Everything that multiplies by 7 has to be negative 5? No. So that doesn't factor. So that we don't have to worry about that happening. So that should tell us, well, nothing's going to simplify here. So I'm just going to go ahead and distribute that out. And then on the bottom, I'm just going to simplify like terms and get x squared minus 5x plus 5. And that doesn't factor either, so I know that that's my composite function. What do I know about that? Just a review of rational stuff that we did last week. Is there a horizontal asymptote? Where at? 3/1. Same degree on top and bottom, so ratio of the leading coefficient. So there would be a horizontal asymptote at 3/1. We're going to find out something about the vertical asymptotes in just a second as we're finding domain of that stuff too. So let's look at the domain. So domain of f would be what? This is the easy one. Good job. All real numbers. Negative infinity, positive infinity. Ever how you want to write that down, it doesn't matter because that's not what we need. We need the composite domain, not those, but we're using them. Okay, now the domain of g of x, maybe not as nice, but not too bad. X can't be what? 2. All right, so here's what we got going on. The one we're plugging into has a restriction. So we got to know what we're plugging in with. When is it equal to 2? That's the question we've got to answer. When is g of x, not g of x, f of x is what we're plugging in, equal to 2. So we said x squared minus 5x plus 7 equal to 2. And solve that. Which we've been solving polynomials. This is quadratic, so this should be a little bit easier. How do we solve that? Get it equal to what? 0. Because I would love for that to factor. And, we should see something, pretty familiar there. We see x squared minus 5x plus 5. Where else does that exist? The denominator of our composite function. It won't always match. That's what I want to kind of emphasize here. It won't always match that. Because, if something would have simplified, we could have lost the parts of the domain. So when you're looking at domain, remember when we're doing rational functions, domain had to be done before you simplified. So that's why we go back to the original functions to find our domain, not just the composite. Because you may have simplified the composite. So that's why we got to go back here. And then we need to solve that. We already know that won't factor. So what are my options to solve that? Quadratic formula is my number one option most of the time anyway when I'm solving a quadratic. So let's do that. X equals negative b plus or minus radical b squared minus 4ac divided by 2a. And simplify that. So 5 plus or minus the square root of 25 minus 20 would be 5 over 2. Are those real solutions or complex? Real. So that means that they're important places. If they were complex, then you don't even have to worry about it. That means there's no restrictions on it. Okay? Because remember, complex doesn't show up on domain. Okay, so those are our two spots that are problems on the domain of our composite function. So when we go to write that out in interval notation, we need to kind of know which one's the lower number. Which one would be the smaller number? 5 plus radical 5 or 5 minus radical 5? Minus. It's going to get the smaller. So when I write my domain for the composite function, composite was G composed with F. G composed with F. We're going from negative infinity to 5 minus radical 5 over 2. And then from 5 minus radical 5 over 2 to 5 plus radical 5 over 2. I didn't give myself enough room. cheat a little bit here. And then from 5 plus radical 5 over to infinity. There's our domain of our composite function. Okay. Look at your domains. Think about restrictions on what you're plugging in versus what you're plugging into. Two different things there. Okay. And then sometimes you got restrictions, sometimes you won't. It takes practice, no doubt. There's no substitution for doing these problems, honestly. If you don't do them, you're not going to see the examples you need, the types of problems you need out of that, okay? So we're going to work. You got 30 minutes left in class today. You can work on this and work tomorrow. Try to quiz Wednesday, teach the next lesson Wednesday, and then quiz on Friday morning before y'all's meeting. And that way we're done. We'll cap off the week with that sort of thing. Okay. All right.